Thanks a lot. Thanks, Babushan. And I'd like to thank the organizers, Giuliano, Vlad, and Klimpe, who is not here. It's okay. I will talk about this fermionic chains, quite simple for most of you. And in this context, but the speciality is that I will add long-range coupling and broken symmetries. Basically, the coupling will be allowed to be complex numbers. This work I did with people of the University of Saragossa, the Saragossa gang, Filiberto Ares, who happens to be here, José Esteve, and Fernando Falsetto. Those are based on these two works, and there are others, but those are the already published papers. Okay, so what is the thing about entanglement entropy? How it starts actually in high energy physics, in the black hole physics, where there is this Hawking proof some decades ago that the entropy of the black hole goes with the area of the event horizon. So there are many people trying to understand that. Actually, we are trying to understand what are the stat mech behind this formula. So that was in the 70s. In the 80s, Sorkin and his group, Bombelli, Cohen, Lee, they proposed that the following idea. We take a surface, a spatial surface in this community, how they call it, and in this surface you define a scalar field. And the scalar field. And then you consider a region that it's supposed to model the black hole, and you integrate out the fields. The question is, what is the entropy emerging out of this process? Then they proved that in this case, actually the way to do is to discretize these three fields, scalar field by harmonic oscillators interacting harmonically. It's quite simple. Then they take some thermodynamic limit. This is how it is proven this. So it was proven that the entropy, which is called entanglement entropy, is the volume or of the boundary, which is the area of this event horizon. Now, in 1993, Zrenik solved the same problem, which was a famous PRL, and it got a lot of momentum. Then come a work by let's see, Wilczek, Holstein, and this gang, and then in the black hole community, many works, but also it starts to be done for the integrability, condensed matter. Now it's a whole subject important for quantum computation and all that. Now, so those are the main works. Here there are two techniques. Basically, when the problem is critical, then you can use some CFT techniques. First, there's this work by Vlad in this PRL, but it is quite famous, those papers by Calabrese and Cardi. That's a little bit late after the Corep's paper, and also this other paper. They discuss different notions of entanglement entropy, consider many intervals and things like that. And there is the other way to do it, which is to use correlation functions that you can describe in terms of Toeplitz matrix. And I think the first paper is this by Jimmy Korepin, if I'm not wrong. And then there are many by the group of Keating Metsadri in England, and also EATS has many contributions mathematical. So the work I'm going to talk will be basically using the techniques of Toeplitz matrix that has some, although a bit more complicated, it has some more powerful because it can be extended to non-critical regime. Now, so just to recap a little bit, the notion of entanglement entropy is quite simple and still quite powerful. According to Schrödinger, is the main feature of quantum mechanics. So the idea is quite simple. you can take your Hilbert space and consider the tensor product of two sub-Hilbert space, let's say, bipartite it, and then you consider some vector state, which we call a pure state, that we can represent in terms of density matrix. Now, if you do a partial trace, that means you integrate out with respect to this left Hilbert space, then you got a reduced density matrix. Now, this reduced density matrix, it may not necessarily be pure, meaning that I have to write it as some sum over pure states. There are some technicality that I'm not going through, but then you want to measure this entanglement. There are some ways to measure. The most famous are the Renyi entropy, that is parameterized by this alpha, which has this formula, log of the trace of this reduced density matrix to the power alpha, which is easier to compute than the most known von Neumann entropy that involves the trace of some whole log, and this is sometimes quite complicated to compute. Now, if this entropy is different of 0, then it means that the reduced density matrix is a mixed state. Otherwise, it is a pure state. That is, when S alpha is equal to 0, it's a pure state, and this simply means that I can write it as a vector state in a Hilbert space. Now, there is some, I enter a little bit in this game from some conceptual things that is typical in high energy physics community or quantum field theory, that there is a different way to describe a quantum system instead of, which comes from the algebra of observables, which basic in terms of the chains are just the spin fields or the Fermi fields. So with them we can form all the words that you want, and this will define this algebra. And there is a state, which are all correlation functions that we want to compute with these words of fields. So if you know all the correlation functions, there is a theorem given by this GNS construction, which is called by Gelfand, Naimark, and Siegel, that I can reconstruct my Hilbert space and the state as a density matrix. So the point is that sometimes too, it's not clear how to perform the partial trace. For instance, if I want to perform the partial trace and still preserve some symmetries, like the exchange symmetry, the statistics of my fields, usually the partial trace, it doesn't fit well, then it was not clear then how to do it, and then we propose a construction based on these reconstruction theorems that the partial trace can be replaced by the notion of subalgebra, some subalgebra of our fields. Then the restriction of this state, the initial state, if it is pure, to the subalgebra, and do process this nice reconstruction, then you can have the same notion of entanglement entropy. This is quite nice conceptually, but up to now, from the point of view of computation, it's not so nice. I mean, I've seen many talks about how to compute all correlation functions, and we know how complicated it is, because unfortunately this depends on this case. Now, but when I have a system that is quadratic in my fields, in this case, I take a quadratic fermionic chain, then the previous problem can be simple tackle, because I have a weak property, that it is enough to know the 2-point correlation functions, and then I can reconstruct, I can obtain all correlation functions, and then this works, okay? So the problem that I'm going to work is quite simple. Just a quadratic fermionic chain with longer-range complex coupling, in a chain with size L, n sides, and n spinless fermions. Our result is that we obtain the closed formula for any point in the phase diagram, any point, not only critical points, for the Rényi entanglement entropy of the reduced density matrix of an interval that has size x. So, and only one interval. We have a formula for that case. Okay, this is what I'm going to talk. Now, so in this case, the most general Hamiltonian that I can construct is this one, quadratic, only quadratic. Then I have the first Hoping terms, but with distance, long-range distance, this is small l. I have also the generalization of the superconductor terms, where all these A are fermionic fields. A's and B's can be complex, and they satisfy this condition so that the Hamiltonian be Hermitian, and it can be, yes, all interact with all. So, see, if you should here from minus L to L, L can be is some up to n over 2. And I'm considering periodic boundary condition. Okay, there is still could consider other boundaries condition, but we have not considered so far. This is already complicated enough. Right, and then see if this generalization of the superconductor terms is equal 0, then we have fermion numbers are preserved. This is what I'm talking about symmetry, breaking symmetry. So the imaginary part of my Hoping terms break reflection symmetry, or parity symmetry, if you like, and the imaginary part of B breaks conjugation symmetry, charge conjugation symmetry. So this is the most general thing, and the complex part is our construction. I will. Examples. Now I'll give lots of examples. Some, for instance, if L, capital L, here is equal 1, then I have nearest neighbors coupling, and if I have a gamma, I'll have the superconductor term. It used to be known as XY chain. Now people are calling Kita F chain. I don't know why, but anyway. This was the first time I heard of it. I mean, I know it's this paper by Lipschutz and Mattes. There is an S missing. So this is the known Hamiltonian. I mean, we learn in school. And this is the dispersion relation. The known one depends on H and gamma, which are the parameters of the system. Now, there are critical regions. And there, in this critical region, that is the spectrum is gapless, and then we can have a CFT description, which happens when gamma is equal 0 and H is less than 1. And when H is equal 2, actually this should be 2, sorry. C equal half, which is a free fermion. Actually, I can write the diagram here for you. So this blue line corresponds to some free fermion, and this to some free bosons. But then I have all these non-critical regions, and there is this line, this curve that is known as Baruch-McCoy lines, and this dashed line is associated to some entropies that will come in the next page. Okay, this diagram is with the entropy is a construction of each Gini correctly. And here are the formulas. So I have here this region below this ellipse of Baruch-McCoy is the region 1b, here is 1a, and here is region 2, which was missing, right? And here are the formula, complete formula, and they depend on this elliptic integral defined here. So here are and there is this cross ratio that I define everything in terms of these cross ratios. So these are the formulas. Now, there is a generalization of this, which is adding complex coupling to the Hoping terms, is the Jalodziński-Maria coupling, next Nibos coupling, L equal 1, but now I added this term to the Hoping term, so the Hoping term is complex. And reflection symmetry is broken. Say it again. it can be also, but yeah, there is also these Pyers, dimers, yes, this kind of thing. Yes, this is also possible. Yes, it is, we consider it as we have been discussed that a minute. There are critical regions. The critical regions happens to be blow-ups of in the algebraic geometric sense of the previous diagram. Just to recall, this is this previous diagram. The new diagram, the critical regions is a kind of a blow-up. It is this region here. So the entire region has some CFT associated to it. And these non-critical regions, the physics goes as the usual XY model. So there is also here some ellipses here of a constant integrals and all that we have constructed. This is our one of our results. What else? Yes. One thing that actually we are interested in, so far we could not do, just for the sake of your information, is that we don't have an analytic formula for this, for similar curves of constant entropy in this critical region. But you have numerics of it, so we are finishing this, just this. And we'd like to see how is the matching, but there is no matching from the non-critical to critical region. So this is studied. So here are the formula. These are our formula that we construct. And for the non-critical region, basically, the length of the interval that I'm a block of fermions. I can associate to spins by the Jordan-Wigner, but when it's this is block of fermions. I have to integrate out my chain, but this is a fermionic chain. So yeah, I just integrate out. I trace out this interval. Yes, yeah, and the rest of the world. Okay, not X. Okay. Okay, so this is our result. Another example is if we add to the kita F chain some long-range coupling that decays like this L, this distance. No, the long-range coupling is decaying according to this exponent. So we can also work the spectrum, and it will depend on some polylogarithm function. So this also we work. We also have the spectrum, and we also have the entropy. Here, the entropy, on the logarithm part of the entropy, because the logarithm of x, the coefficients in the white range is 0. There is no, it is non-critical then. But in the gray region, it can be half, and in this black region, can be 1. Okay, that is our cooking. We can even be going further, and then we can consider long-range chains and depict it as in terms of ladders. For instance, this Hamiltonian that has this nearest neighbors, next nearest, and then this n/2, this long range, I can depict it like that. It's called ladders. So we can consider this ladder Hamiltonian and integrate out or trace out this x. Then we got this kind of formulas. That depends on x, on log of x, and this is that. So these are, and we also can consider other ladders like this one, with q, the distance, this 3, and we can even consider more things. I mean, just to show that our results can be. Yes, yes, yeah. That I don't remember. I don't remember. No, B alpha, yeah, B alpha is some integral that is of associate to complicated. I will show in the next, this formula will appear in the next. It's complicated because it depends on some, I'll answer your question in due time. So, I mean, just to say that we can do all of that, okay? These are simple and there are, I mean, we have the formula. Now, how do you work on that? I mean, those are the results, how we work with that, how we obtain this formula, what is our construction. Basically, the construction is the following. These are the main steps. Of course, each step is complicated, but this is what you have to do. Find the dispersion relation, construct Fock states. This is simple. Then we obtain the 2-point correlations, in our case for the ground state, but in principle we can do for any state. And write the entropy formula in terms of the eigenvalues of the 2-point correlation function. 2-point correlation function as a matrix, it has its eigenvalues, and then we write the entropy formula in terms of these eigenvalues. Now, these eigenvalues is associated to the determinant of the correlation function, so we write the entropy formula as the determinant of the correlation functions. That is a Toeplitz matrix because of translation invariance. So we write the entropy in terms of this determinant. Once you have the determinant of this Toeplitz matrix, the correlations are the Toeplitz matrix, then we call the asymptotic formula that comes from Fisher-Hartwig theorems, and it's the generalizations. For instance, if it would be, I show, if it should not block Toeplitz, a simple scalar Toeplitz matrix, then Fisher-Hartwig theorem is enough. But usually to be a block Toeplitz matrix, I will show to you what is that soon, and then we don't have a general theorem, and then we have to work case by case. So let me then follow these steps. No, then so I'm given that Hamiltonian, then I use the Fourier series that with the discounts from periodic boundary condition, the usual thing, and then I write the Hamiltonian in this formula, in this way, with these fermionic modes. Now, I want you to pay attention that the couplings of my Hamiltonian, they enter in these functions in this Hamiltonian. So, and L here is because of the long-range couplings. Okay, so here is A and B from my Hamiltonian. Then I write the dispersion relation after some Bogoliubov transformation. Then I have this S and A defined here, what S is up, A is down. And I will set some Fock vacuum, which are annihilated by my Bogoliubov transformed fermions. So a general state is some subset of these integers, okay? That is the usual construction creation out of the Fock vacuum. So, and then I have my entropy, my energy defined like that, and these are the states that belong here, the numbers that are here, and numbers that are not here. So I can write this in the thermodynamic limit as a density of states. Now, the 2-point correlation functions, I write in this basis as a 2-by-2 matrix times a matrix of n of 2x or x by x. So I have a 2x by 2x matrix defined like that. Okay, this is just the 2-point correlation functions. Now, if I compute the eigenvalues of this matrix, then I can plug in the formula for the Rayleigh entropy, and I have this formula where the eigenvalues ni are the eigenvalues enter here. Okay, this formula is quite complicated. It doesn't look like, but it's complicated to compute it in a closed form, right? And it's not computational efficient. It's not good. Yeah, it's a big matrix. There are 2 by 2 matrix, tensor product with the whole n by n or x by x in this case. Huh? Oh, we can do it. I mean, you can do it. You have done it many times. Okay. No, this part, I mean, up to now is formal. It's a toplet, it's just a simple thing. It's not complicated up to here. Then what is complicated and with no hope computational is to do this summing. That is quite complicated. But then, there you know, you're from Russia, and there is this FADEV. I learned in the books, because that if you have some difficulty, you write your problem as a determinant. So I will write this in terms of a determinant, and determinant I can, I know how to solve sometimes, so I have some formula. So I write that formula, which is, I just put in this function here, so define it here, which basically is this function, okay? Sum here, and using the residual theorem, I can write it like that, where this derivative of the determinant of this Toeplitz matrix, because this is a Toeplitz matrix, if I subtract some unity, it will be still a Toeplitz matrix, then I have only to compute these determinants, where each zeros, or each poles, will be lying these in the real line, like that. These points are this. The eigenvalues of V of x are sitting these points. So I integrate, this C is this contour. No, logarithm of determinant. Logarithm of determinant, sorry. How I'm defined x. Sorry, otherwise it doesn't make sense, because I have to have something down the stairs to get the poles and then compute the residue. Yeah, so sorry, mistake, my fault. Okay, anyway, so now I have this formula in terms of a determinant. Now, this is a Toeplitz matrix. Toeplitz matrix is that the diagonals have all the same numbers. These are the equal numbers here. And block Toeplitz, it's when I have these are the same numbers, but these are different, but always in the diagonal, like that. Okay, these are block Toeplitz. For this case, we have many theorems that starts with Sego in the orthogonal polynomials and goes to Fischer-Hartwig theorems. Also, Lienard in the 6th has some, before Fischer-Hartwig, some theorems on that. So those are simple. But then for this case, we don't have general theorems. We have to work a bit hard. So, now that I told you that this V of x is a block Toeplitz of this form. Actually, I can take this Fourier modes like that, and this JK is called the symbol of this Toeplitz matrix, or the generating function of this matrix. And this symbol, this generating function, of course, because this depends on the state I choose, I can write for the case of the ground state, the usual ground state, that I have the numbers that makes the density. I fill the Fermi C, I fill the Fermi C to construct this ground state, and this usually to have this form here. So it will be some this unit matrix 2 by 2, then some complicated matrices and unit again. Okay, this is complicated things. But then for the case of this Toeplitz, when it's scalar Toeplitz, this is scalar Toeplitz again, and this is block Toeplitz. For the case of scalar Toeplitz, there are these theorems. These theorems, although they are quite technical, they have a very simple message. The message that we can have the asymptotic information of the eigenvalues, or the form of asymptotic formula for the determinant when the n by n matrix, this n goes to infinite, I can have it, and it should depend only on the analytic properties of the symbol g of theta, where this g of theta is the thermodynamical limit of this j of k. So it only depends on the analytic properties. This is quite interesting. For instance, if I have some scalar symbol for the scalar block tuplets of this general form, we have some smooth function, psi of theta, and I have jumps. These are just jumps described as this beta r, which is just things like that. This is beta. So this is a way to codify these jumps. I can compute the asymptotic of my determinant, and then I plug into the formula for the entropy, and then I integrate. When I do that, I will have this general expression. Some piece that depends on x, on the length of my interval that I'm integrating out, some piece that depends on log of x, and some constant terms, and then some extra terms, 1 over x in general. Now, this guy here, this log of x, they are associated to CFTs. Usually there are some CFTs, and they depend on the existence of this beta r, of these jumps. This guy, it doesn't depend on this discontinuity, these jumps. And this is, we call this associated to volume law. And this is the rest to area law, if you like. So that this is that B alpha that Vladimir was asking. These are the B alpha, but it is associated to some integration coming from the asymptotics of my determinant. I'm avoiding writing complicated expressions, but I mean, we can do it. It's not so complicated. Anyway, these are some mathematical reference. Bastor is Stella Bastor is the name in this game, the famous Fischer-Hartwig. Also, Widom has some theorem for block tuplets, and more recently, this Deift, Itz, and Krasovsky, they have been working on using Riemann-Hilbert's techniques to compute those the things, which actually the kind of technique that I'm going to use. No, this comes from the density of state. This you can think of the density of state, for instance, for free fermion. I mean, if I do, yeah, for instance, just like density of states, G theta, for free fermion. It's just some half-side function. So there is some jump here. This is one example, and then I'm writing a funny way, just because this makes simple to use the analytical power of complex analysis. The firm C. Okay, this is the simple things, the simple example. But I can have many of these jumps depend on my state. Okay. Thanks a lot. Okay. Now for the block tuplets, that because V of x, this correlation function is generically a block tuplet, there is no general result. These are general results for scalar tuplets. Then those F and G that I said to you, it depends on the couplings of my Hamiltonian. I have some conditions that in those cases the symbol is continuous, this symbol is continuous, and the formula found via Riemann-Hilbert's problem by Itzjin Korepin for the XY model, which is nearest neighbors, and Itzmet Sadri-Mo for long-range coupling. They have them. For some other case, the symbol has some discontinuities, then this is our cooking, and then we show, for instance, our examples, we show that the discontinuities, because I have a matrix, it's quite complex. I have matrices come from the other side of these jumps. And if they commute, then we can have we construct a formula, and then we check it numeric. Actually, Filiberto checked it numeric. He's good at that. So let me remind you, if time permits, yes. Let me remind you, or show to you, if you don't know, how to work in the first case. This was in its Jim correct for XY model. So this is the prototype, and they have to use the Riemann-Hilbert techniques. This is a nice reference, quite pedagogical, but you can see in the chapter 13 or something like that in the book of this conference. So we write this is just a flashing of the technique. I'm not going to do this because it's quite involved, technically involved. Then, I want to compute the asymptotics of this determinant when x goes to infinity. So the first thing is to turn this problem into a Fredholm determinant. So this determinant I write as a Fredholm determinant. This is just to remind that my Hilbert space is the square integral function over the circle. So this is where this k is some integral operator with an integrable kernel, which has this formula here. These small f and capital F, they will depend on my couplings. All my couplings, I will put it here. Then there is some exercise homework to do and construct this. Now, the nice thing of this integrable kernel is that they form there is some algebraic structure, and its inverse, which is its resolvent, it's also integral. That means there is this R, this resolvent, that has also a kernel with this form. And the whole problem here in this game is to find this function h, these two h functions, as a function of these f functions. They are quite complicated. Okay, this is where we have to work. But if you know this, then we can compute the derivative of the log of my determinant using this formula here. Okay, there's some formula where phi of z comes from my dispersion relation, or it's the analytic continuation of my dispersion relation. Okay, so all I have to do is to find these things. It's easy to speak like that, but it's hard to work on. Now, these h functions I can use some Riemann-Hilbert problem. So I enter into Riemann-Hilbert problem, which are the following. There are these functions, y's, like that solve some Riemann-Hilbert problem. But then what you have to see here is that those h functions, they depend on my f and f of my original integral operator through this solution of some Riemann-Hilbert problem. But what is a Riemann-Hilbert problem? It's some analytical function in my complex space, except in the S1, some contour, that in this case I'm choosing S1, and in S1 I will put some boundary conditions that we call jump matrix. So my function come analytically, reach this contour, and something happens and turn into another analytical function on the other side. This is it's quite, for all of you we're experts in inverse scattering problem. This is the inverse scattering problem. So they are analytic like that. This is some technical condition. It's not important now. But what is important is this. For instance, from one side, I turn to a function the other side through this jump matrix, this boundary. And this jump matrix, they are constructed in terms of my function of my integrable kernel. Okay, this is the nice thing here. Then I only have to solve here, and this is where things get really complicated. Really complicated. Okay? to formulate this, now it's complicated. Then you call some nice mathematician, they do it. Or God talks to me someday, hopefully, and tell me what is the solution. Okay, that is the... Anyway, in this each is gene correct, they could solve this problem. And also each metadre mode, they also solved for the long range case. And we solved for the same problem for when there was complex coefficient couplings. Okay? So, by solving, in the case of XY model, for instance, we can write this in the end in terms of some Jacobi theta functions. Okay? It is, I will try to convince you why you have some Jacobi theta function. This is a formula. And the reason is that the density of states, where I would use to construct this Riemann-Hilbert problem, it defines some torus in some Riemann surface in some torus, which is given by these functions. Here is the torus that I'm constructing with these 4 singularities and the branch cuts here. What's a beautiful thing here is that if I start to change the location of these singularities, I start to change the modulus of the torus. I change the torus. And this corresponding to change my point in my phase space. In that phase space that was, for instance, in the case of XY, it was defined by gamma and 8, the anisotrope, the superconductor term. And so I change gamma and H, and I change the locations of these singularities. And then I change what is the algebraic curve that I have. That is. So, since this is a torus and elliptic function, so it's natural to parameterize my problem in terms of theta functions. That is the... Yes, 4 degrees. No, this is elliptic function torus. For the case of elliptic curve. This is elliptic curve. For the case of long range coupling, we have hyperelliptic functions. Actually, there is a nice formula, a theorem that we wrote in one of those, in the second paper, that relate the genus of this hyperelliptic surface to the distance, to this long-range interaction, which I'm calling L. So there is the formula is G is equal, the genus of the hyperelliptic surface is equal to 2L minus 1. This is our nice nice result. So that is this. Now, so this is the known stuff it was already known. In our case, we are in this other case, which happens when you have this complex coupling. Then the 2 by 2, we have this 2 by 2 symbol, G of theta, and has some discontinuity, these jumps. Okay, and we are assuming there when it comes from a matrix come here, the other matrix come here, but we are going to assume that these matrices, they commute. Of course, we have to check in the actual model, but there is our problem. If they don't commute, we still don't know how to solve the problem. So if they commute, then we can, for this Topliss determinant, we have this formula written here. That depends on the log of x and this b of x, g, that I define here, and I will show you in the next slide. And this part that depends on the size of the interval. Now, how we solved it? We analyzed what were all possibilities, the variety of possibilities for the jumps, that come here. And these are the structures for looking at the density of states. We analyze the density of states, and you classify the density of states, the kind of jumps. So each kind of jumps, then see, there is a matrix M and some the identity, 2 by 2 identity, then back this kind of example. Then here are the formulas for these cases. So we analyze this. Summing up this analysis of this discontinuity, you see that the total B can be sum of, there is only one value with M to I, and then we have this general formula. Here is our. This is what we use to compute the Jalodziński-Moria case. So this is our formula that comes from Jalodziński-Moria case. Okay, and where this is some integral, this is simple integral. Now, yeah, this is the integration of alpha. Yes. If I solve this, I will obtain this. Now, then in the second paper, we, using all of this, we decide to study the following. Each point in my elliptic curve corresponds to a point in my phase diagram. So if we start to move to see what are the symmetries of my elliptic curve, we may see what try to extract some physical consequence of my phase diagram. So, for instance, then this is in the elliptic curve of the torus. It's natural to consider Möbius transformations. So we consider Möbius transformation, but then we ask what are the subgroup of Möbius transformations that live invariant, those determinants and hence the entropy. These are, so this subgroup is this SO11 of the Möbius transformations. And for instance, these 2 points here, and these are singularities in XY model. So it defines some point in the diagram of XY model. So we start to act with this SO11 because they will keep the entropy constant. And you see that there is this beautiful flow, just like some RG flow, that you see they will change until they go to this point, which is a stable point, which corresponds to the essential singularity that H is equal to and gamma equals 0. Okay, and then this analysis we have we did this analysis in the second paper in the others. We also consider in the second paper some dualities in this XY model. So we see these are some curves where the entropy are kept constant. You move along these curves and the entropy is constant. This is like this, moving along this flux here, this flow, the entropy is constant. Now, what we found is that besides this, some points here, they are related to each other by some kinds of dualities. There are 2 kinds of dualities we consider. For instance, these 2, the entropy, the entropy is the same here in between these 2. This is the duality, is this modular transformation or Dehn twist. And there is a relation between these 2 here, this here, and this is a Kramers-Varnier duality type. So we can classify all of that, and there is a sort of triality that these points, the entropy here is equal to the entropy in this point, in the region 1A, and this other. And there are all these. But then we extended this to the hyperelliptic case, to the long-range interaction. So that is basically our work. Muito obrigado.